And this is our most important topic related to statistics, basically regression analysis. Our exposition here will be just the basics. We call it the method of least squares. A much more detailed treatment will be available for those of you who are interested in our statistical analysis in finance course, which is Finance 8302. So, but at least what we want here is to have a basic understanding of the topic. And the idea is to fit a straight line to a set of given data points. So here we have two parameters, x and y. I have a plot here. So here we have made multiple observations. So this is observation 1, observation 2, 3, 4, and so on. So we have multiple observations that we want to fit a straight line through them, right? So in this example, it seems we have 14 observations. For instance, we can just pick one of them randomly. Let's say, for instance, observation 6. So this is the x value associated with observation 6. And this is the y value associated with that observation. So in total, we have 14 pairs of observation, starting with x1, y1, all the way to x14, y14. So we postulate a straight line that will, or we call it a line of best fit, that will fit into these data points. And the key idea here is, I think we can eyeball and see what is so special about that blue line. This is our line of best fit. So the key idea here is that we are trying to make the deviations between the observed values and the corresponding points on the fitted line as small as possible. So what does that mean? So it means, for instance, for observation 1, how far is it from the line? Observation 2, how far is it from the line? The same thing for observation 3, 4, 5. So we are checking those vertical distances between the data points. Oops, I think I skipped 9. Between the data points and the straight line. It seems the last observation is exactly on the line of best fit. And the key idea is to minimize the sum of the squares of those deviations. So those red deviation lines, those distances, red distances, we square each one of these, we add them up, and then the line of best fit should be the one that minimizes that sum of squared differences. I hope that's clear. And it turns out, because it's an optimization problem, let's write down the objective function. So we are technically minimizing the sum of squares of those error terms, right? And that's just, we are, for instance, we are y1 minus, so this would be the data minus the corresponding point on the fitted line is just y1 hat. That's, we are squaring this. So does that make sense? So basically what I did is just on the picture, for instance, if again we look at the sixth observation, the associated point on the line would be this point over here. So this is y6 hat. So as a result, the difference between y6 and y6 hat will give you the length of that red segment over here. The red segment, the distance, the deviation, how far is that observation to that blue line, right? So the goal is to find the equation of that blue line, right? So that blue line here, that's why we are trying to estimate. And as you guys all know, that line will have two parameters. So you need to tell me the slope of the line and where it hits the y-axis. Based on that, I can tell you how to draw that line, and we can easily fit it. So that's the key idea. But in order to accomplish that, to find those two parameters, the slope and the intercept, we need to optimize this. So this is plus, so we have a few more terms here, right? Same thing for the second observation, and so on. For all of these 14 observations, we are looking at those deviations, squared deviations. We add them, and we want to minimize this sum. Does that make sense? Or if you want, in a technical language, we will put a summation sign. The sum of all these squared differences, where I runs from, in this example, 1 through 14. But in general, we will have n data points, so we will just write an n there. But wait a second, y hat is... the way we calculate y hat is through that model, right? So we can replace it with the equation, basically. So what comes out is yi minus beta 0 hat plus beta 1 hat of x times x, I should say, square. Does that make sense? So this whole thing is yi hat. And that's it. So I equals from 1 to n. So we are minimizing that sum. So it turns out it's a rather straightforward business. So we are minimizing with respect to beta 0 and beta 1. Technically what I'm doing is, if I'm using calculus, to be honest. So we are taking the partial derivative of the sum of squares of these deviations with respect to beta 0 and set it equal to 0. We'll get an equation from there. And then we'll do the same thing for beta 1, partial derivative, set it equal to 0. When you solve this, and I'm not going to do that, in any mathematical statistics book you will find it, so I will put it on the video description if you are interested in the details of this calculation. So basically we use calculus to take those derivatives, very straightforward calculus as a matter of fact. And ultimately, after having used calculus, the final outcome turns out to be the following. So we can calculate beta 1 hat and beta 0 hat by the following formulas. For beta 1 hat, the formula turns out to be, okay, so I will simplify it. It is something like this: sxy divided by sxx. And for beta 0 hat, that one is even easier. So once you find beta 1 hat, you can just substitute into the equation, into the linear equation. So beta 0 hat will end up being y bar, the average, minus beta 1 hat x bar, where y bar and x bar are the averages of those variables. That's it. So that's the solution to the beta. So now we need to explain what sxy and sxx mean, where, okay, let's explain that, where s sub xx is simply equal to, let me write it, it is the following, and I'm sure you guys will remember this from the covariance. When we calculated the covariance matrices, y bar, again, I equals from 1 to n. And for sxx, sorry, this one is sxy, I should say, sorry for that. This is wrong. For sxx, the denominator here, so that would be simply an expression akin to variance, which is minus x bar square equals from 1 to n. Let me be a little bit more clear here. This one, usually, that's one way to calculate it. Alternatively, we often find ourselves if you expand this whole thing, we often find ourselves using the following alternative form as well. So you guys will be deciding which one is the most convenient one to evaluate the desired result. Xi equals from 1 to n times the sum of yi equals from 1 to n. That's it. Well, actually, there's also an alternative form for this one. Let me also quickly write that one out as well. So I equals from 1 to n, x sub I squared. After you square this expression, if you do the algebra, that's what comes out. 1 over n, the sum of I equals from 1 to n, x sub I squared. There you go. So what we will do next is, well, this is a very ugly looking formula. In practice, you will almost always use Excel to do these calculations. But what I have in mind is I will provide you an example where I will use paper pencil to go over this. But right after this video, in the next video, I will also show you how Excel can be utilized basically to do pretty much all the calculations in a much faster way. All right, so here's our example. Multiple questions, 5 questions, so it's a long example, and that's pretty much your assignment for this week. Use the method of least squares, sometimes also referred to as regression analysis, part of the regression analysis toolbox. The method of least squares to fit a straight line to the 5 data points given, right? X, when x is -2, y is 0. When x is -1, y is 0, and so on. So we are given these 5 pairs of data points. And first we want to find the slope and the intercept of the line of best fit. In fact, let me just go ahead and directly draw it. I guess shouldn't be too hard. Oh, how did I manage to do that? Okay, so it was strange. Somehow I deleted the line. There we go. So this is the x-axis. So we have -1, -2, 0, 1, and 2. And this is the y-axis. So we are told that the largest value of y is a 3. And here are the data points. So we have at -2, y is 0, the first point. At -1, y is still 0, the second point. Let me put a couple marks here. So 1 and 2 marks here. At 0 and 1, y is both 1. So let's just go ahead and do that. So 1 and 1. And finally, at x equals 2, y is equal to 3. Up there, actually. Let's just make sure we eyeball it correctly. So somewhere here. Okay, good. So the final step is to draw that line of best fit. So I'm just eyeballing it here. I have no clue how the line will look like ultimately. Which color should I use? Light blue. So something like this, I would say. Do you guys agree? Okay, so this, or maybe a bit lower than that. So let me just go ahead and select it. And let's just shift it a little bit down. Maybe too much. Okay. So, I don't know. So that's exactly the line that we are trying to fit, right? So beta 0 hat plus beta 1 hat of x. So evaluate beta 0 and beta 1 by using the given formula. So that's the first question. All right, so that's because once we have beta 0 hat and beta 1 hat, that will give us the equation of the line of best fit, that blue line, and we would be done, right? Okay, so what I will do is let's scroll down. I have it in a separate page for each one of them. I think it might be useful to just rewrite the numbers. I didn't think of that, sorry for that. So I'm rewriting the 3-line table. There you go. And the y values, corresponding y values were 0, 0, 1, 1, and 3. All right, there you go. So again, so our goal is to find the estimators beta 0 hat and beta 1 hat, right? And I already gave you the formulas in the previous video. In the previous step page, I should say. SXY divided by SXX. And beta 0 hat was even easier. So once you have beta 1, so it is just, I need more space here. Let's put it right here underneath. Okay, there we go. So it is just y bar minus beta 1 hat x bar. All right, so the natural starting point is to first calculate SXY and SXX. And once we have those values, we should be able to calculate the desired values as well. So what I will do is, I will be smart. I will just take this table. And look what I'm going to do. I'm going to put it right underneath. And usually in Excel, I'll do the same thing. Extend the table and construct just the values that we need. And the additional values that I will be needing is, so these are the xi and yi values. So this is I, the first observation, second, third, fourth, and fifth. We have 5 pairs of data points here, right? So I will be needing their sum products. So, well, the products first. So xi times yi, that one is 0. So -2 times 0 is 0. -1 times 0 is 0. This one is also 0. 1 times 1 is just a 1. And 2 times 3 is just a 6. Another one that I will be needing is xi square. So squaring this column, xi column. So we will get a 4, a 1, a 0, a 1, and a 4. All right, so having done these, now we can even calculate the sum of each column. Let me just scroll it up a little bit. Sum. So the sum of xi values, if you add them up, that will be 0, I think. The sum of the yi values, 0, 0, 1, 1, 3, that's a 5. The sum of xi, yi values, that's a 7. And the sum of the xi squares, 4, 1, 1, 4, that's a 10. There you go. Okay, now we are ready to calculate s sub xy. So the numerator first. For the numerator, I'm going to use the shorthand version, the second formula that I presented somewhere, this one. I'm going to use, like I said earlier, in general, we use the second version. So either one works, but this one, it seems, will work as better for us. And for that one, in order to use that, all I need is this one, which I already calculated, the sum there. We already calculated the sum here, and we have the sum here too. For sxy, I will do sxx, I will do the same thing, because I need to calculate, I need these numbers. All I needed was the sum of squares for xi's, which I already calculated. So basically, I will need this. And inside the parentheses here, both of them are already calculated. So let's just plug into the given formula. So let me just rewrite it. And then now, so the sum of xi, yi minus 1 over n, the sum of xi's times sum of yi's. And in the denominator for sxx, it is sum of xi square minus 1 over n, the sum of xi square. There you go. Okay, so therefore, the sum of xi, yi, it's this one, that's a 7, minus 1 over, we have 5 data points. Sum of xi's, that's this one, 0. Sum of yi's, that's a 5. Well, because of the 0, it will be irrelevant, that one. But okay, let's just finish it, I guess. Sum of xi squares, that's the 10. And minus 1 over 5. Sum of xi square, so 0 square. So in the numerator, we have a 7. In the denominator, we have a 10. So for the beta 1 hat, we got 0.7. Does that make sense? 0.7. So that's our value for beta 1 hat. That's the slope parameter. Now for the intercept parameter, so this one is equal to, sorry for that, y bar, which is basically the sum of the yi's divided by number of observations. Let me do it in 2 steps. Sum of yi's divided by n minus beta. So that one is, we already calculated, is 0.7. And x bar is the sum of the xi's divided by n again. N is 5 in our example. So sum of yi's is a 5. 5 over 5 minus 0.7 times sum of xi's is 0. 0 over 5. And indeed, this is just a 1. Does that make sense? So that is the value for beta 0 hat. As a result, the fitted line is basically y equals, or y hat, right? Is equal to beta 0 hat plus beta 1 hat of x times x, I should say. Beta 0 hat is 1 plus beta 1 hat is 0.7. So 0.7 times x. That's it. So that is the fitted line to those 5 data points given. Now in the next step, so I will just, so this implies that. So in the next step, we will need to find the variances of these estimators, beta 0 hat and beta 1 hat. It turns out we can express them in terms of sigma, the standard deviation, the population standard deviation. And the formula is, again, can be calculated, derived, pretty straightforward. It's long bash sheet things. So what I will do is I will give you the formula for both the variance of beta sub 0 hat and beta sub 1 hat. And these are the following. So the variance for beta 0 hat, the intercept, the y-intercept, it turns out to be sigma square, the sum of xi squares, again I is running from 1 to n, all divided by n times s sub xx. That's it. The variance of beta 1 hat, the slope parameter of that straight line, turns out to be just sigma square over S sub xx. So from the previous discussion, we already calculated every single one of them. So, well, except the sigma. We will talk about sigma in the next problem. So sigma squared times, so the sum of xi squares, the xi squares, the sum was 10. So let's just plug it in there, times 10. And, oops, that's a 0. And n times, n is, we have 5 observations. Sxx, what was Sxx here? Sxx, the denominator came out as 10 minus, so the denominator came out as a 10 actually. So that one is a 10 as well. Well, the 10s will cancel. So that's just 1/5 of sigma square. That's a 5, believe it or not. Let's put the 5 properly. And so, like I said, so the only way we can at this moment express beta 0 hat and the variance of beta 0 hat and beta 1 hat is in terms of sigma, but we will handle sigma in the very next problem. Let's quickly finish this one as well. Sigma square divided by Sxx was 10, like we said, and that's pretty much it. So if you want, we can write it as 1/10 of sigma square. So this problem was here very straightforward. And one more thing I can mention is the question is only asking for variances, but I can also quickly check the covariance between these two, beta 0 hat and beta 1 hat, just for the fun of it maybe. And the formula is this, minus x bar sigma square all divided by Sxx for that one. But the good news is x bar, check this out. X bar is the sum of x's, which is 0, divided by 5. So, so minus 0 over 5 sigma square, all divided by Sxx, which was just a 10. But it doesn't matter, right? Because of that 0, everything will vanish. So the covariance between beta 0 hat and beta 1 hat is just 0, thanks to the fact that simply because x bar is equal to 0, but x bar is equal to 0 itself because let me just actually do it in one step. I don't want to say because I don't want to explain the reason itself. Xi, the sum of xi over 1 to n divided by n, but the numerator itself is 0, so that's why this was 0. Awesome. So now let's attack the sigma itself. So how can I estimate sigma square? It turns out again there is certain formulas for that, and it turns out that the formula for sigma square, the estimator for sigma square is the following. It is s square itself. Estimate sigma square by s square. That's it. So the sample standard deviation will be the best estimator for that, and as a result, s square, the formula for s square is just SSE, the sum of squares of those error terms, divided by n minus 2. In our case, n is equal to 5. So all we need to really calculate is the numerator, SSE. So how do we calculate SSE? Well, you just plug it into the equation, right? Remember at the very first step how we described SSE. Here, SSE is just the sum of all these values. In our case, we have 5 data sets. One by one, we can calculate y1 hat. We already know y1, y2, y3, right? Those are the given data points. It turns out that there's okay, let's just do it here. There's a really fast way to do it, and I'm going to do it that way. So basically, it's the sum, like we said, of yi minus yi hat, so squared, right? Well, in this case, the hat is the sample mean, right? And that's just, let me write it in long form. So it's just y1 minus y1 bar squared plus all the way up to y5. We have 5 observations in our example. We have 5 data points. There you go. Turns out, if you do the algebra here, there's a fast way to do it. I don't want to do it one by one. That will take too much. Well, it turns out in Excel it's the same thing. It's actually easier in Excel to do it this way. But if you are manually calculating it, you can directly square this, a perfect square. And it turns out that the result outcomes like this, n times y bar square. And now we can just plug in the values. So yi squared is, well, actually, I forgot to have that one, I think, in my table. Oh, yeah. Okay, let's quickly add another column here. So we're just going to square all these numbers. So 0, 0, 1, 1, 9. So you add them up. So you get 10, 11. Does that make sense? Okay, so the sum of yi squares is 11. Okay, there you go. So this one is an 11 minus 5 observations. The y bar itself is... okay, so what was y bar? Okay, let's go all the way up again. Y bar is, yeah, just the average of these values. So the average of these values, you just add them, which is already 5, and then divide by 5 observations. So 5 over 5, which is just a 1. 5 over 5 square. And sure enough, this comes out as 11 minus 5 times 1 square, which is 1. And that's just a 6. So the SSE is a 6. Now we can substitute. So therefore, S square, which is the estimator for sigma square, is just equal to, like we said, SSE divided by n minus 1, n minus 2 actually. And SSE itself is, what did I do wrong here? Oh, another silly mistake. I'm so sorry, guys. So so the thing that I calculated here, this wasn't the SSE. So SSE is, yeah, I did a really big mistake here. So it is really yi minus yi hat square, right? So yeah, I need to make a small modification here. So what we calculated in this step, I'm so sorry here. So this one is really SYY. Yes, that's SYY. That's what we calculated. Let me just move some stuff in here to the right side so I have a little bit more space. We just basically skipped one step. That's what I'm trying to say. Let's just move this up. Let's just move this over here. And there we go. Actually, you know what? 11 minus 5 is 6. So let's write it like so that it fits. 11 minus 5 times 1. And that's a 6. Okay, so this turns out to be SYY. I'm so sorry. SSE itself, oh gosh. SSE itself is SYY. Okay, that's the formula here. Minus beta 1 hat SXY. And I think, if I remember correctly, SXY we already calculated. So SYY is 6 minus beta 1 hat. We calculated as 0.7 in the previous exercise. SXY, SXX. Did we ever calculate SXY? Oh, yes, we did. In the numerator here, we calculated it as 7. Yes. Good. So yes, there you go. So that one is a 7. So therefore, if you do the algebra here, 6 minus 4.9, and that's 1.1. Okay, so that was the number, because the other number would have been too large for. So 1.1 divided by 5 minus 2, 1.1 divided by 3, that's 0.367. So this is S square, which is a best estimate, a predictor for sigma squared itself. So we would use this value because S squared itself is an unbiased. Let me write that down here. S squared is an unbiased estimator of for the parameter sigma square, right? Yeah, so that's and it turns out when you look at for technical the reason this is true, let me just explain it in parentheses, is because the expected value of the error terms are 0, so on a quantitative side. But like we said, so we will learn the details of this in our advanced statistics class. So having done all this, now we can finally attack I think this is the last problem. Oh, 2 more problems. First, let's attack this one, question number 4. We need to do a hypothesis testing to see if the evidence indicates whether the slope is significantly different than 0. So what slope are we talking about? The slope beta 1 hat, right? So where was our line earlier? Okay, so this line, after we calculated beta 0 hat and beta 1 hat, so this equation came out as 1 plus 0.7x. So 0.7 seems very close to 0. So we want to test that. So we want to see if that slope is significantly different than 0 at the 0.05 significance level. And so there we go. Question 4. Here we go. So we need a hypothesis test, right? So our hypothesis, our null hypothesis, is that beta 1 is equal to 0, and the alternative, we are suspicious that it is significantly different than 0. Not equal. Why? Because beta 1 we calculated as 0.7, so we feel like it is significantly different than that. So now all we need is the test statistic and the rejection region, and once we have those values, we can directly check if we can reject the null hypothesis, basically, and that the the slope parameter beta 1 is significantly different than 0. So how does it work? So so far what we have is the following. Let me just summarize. So we already established that beta 1 hat is an unbiased estimator of beta 1 if the error terms, the expected value of the error terms is 0, and it turns out we need an additional regularity condition, which is the error terms we're expecting them to be normally distributed. With those two assumptions, let me just remind you what we did. The variance of beta 1 hat turned out to be, if I'm not mistaken, it was this: xi squared divided by nsxx, and we just did it a few minutes ago, sigma square, I think it was. Where we do it a couple of questions ago here. That's exactly what we did. So sigma, oh sorry, it was sigma square over sxx. Okay, this one was the variance of beta 0. Oh, sorry for that. So this one is beta 0 hat. Sorry for that. So this one is beta 0 hat. For the other one, the variance of beta 1 hat, and that's the one we will need, it was just 1 over sxy sigma square, if I'm not mistaken. And sorry, sxx again. Oh shoot, again the same error. Here it turns out we can also call them, so this portion here, we can call it as C00. So sometimes this is referred as C00, and this coefficient here is sometimes referred to as C11, and those numbers are important for our hypothesis testing. It turns out that the test statistic that we are going to use will be the following. In our case, we are doing it for B1, beta 1, but it works for both of them. So if you have a null hypothesis, let me just write it. So if H04, okay, let's do it here. For H0, a null hypothesis which is of the following form: beta I, so it can either be beta 0 or beta 1, doesn't matter for both of them, beta I0, so the specified value for that beta value. The test statistic is equal to the following. So Z equals, so the test statistic is Z equals beta I hat actually, minus that specified value, divided by sigma, the square root of CII. There you go. And we already explained what CII means. The rejection region is because if your alternative hypothesis is BI is not equal to BI0, so it's a two-tailed test, and in that two-tailed test where the rejection region is simply such that all the Z's with the following property, the Z bar is the absolute value, so all the Z's such that the absolute value of Z is greater than or equal to the critical value alpha over 2. Yeah, so basically we are in either one of the two tails, so that's our rejection region. Yeah, is there anything else I want to say here? Oh, so where do we get that sigma? We can use basically the same trick that we did in the previous question. So for that, we can use the S square because it's a good estimator. So as a result, sigma, we can the predictor is s itself, which is just the square root if you take the square root of both sides. So we can use it like this format. Does that make sense? I think our test statistic as a result will become, if we replace it like that, I think our test statistic suddenly becomes a student's t-test. So if you substitute the sigma here with that expression that I just showed, with square root of SSE over n minus 2, suddenly we get a new test statistic, beta I hat minus beta I0 in the numerator, and the denominator is suddenly this s square root CII. So that's now quite interesting. Here I call that one as s, right? So that's our s. So it is just basically you replace it with this thing here, and that's it. So that's our test statistic, but the distribution here is a student's t-test, student's t-distribution, I should say. Oh gosh, what am I doing here? Students t-distribution, hold on, distribution with 2 degrees of freedom, with 2 degrees of freedom. All right, I hope that's clear. So as a result, well, oh sorry, not 2 degrees of freedom, my bad, n minus 2 degrees of freedom. Okay, so now we are ready to test this result here. So is the slope 0.7 significantly different than 0? That's what we want to test. So we just plug in the values into the formula, and then we should be done. So because we are doing it for beta 1, so we replace the I here in this formula with 1. So beta 1 hat, which is 0.7, minus beta 1 0, which is the hypothesis test, H0 says it is 0, divided by s times, I think we already calculated s in the previous exercise. All we do is we take the square root of this and plug the square root of that into here. And finally, C11 is this one. So we need to use this one. All right, so let's just plug in everything. So the t-test statistic comes out as, let's just plug it in. So let me just do it in 2 steps. Beta 1 hat minus beta 1 0, all divided by s square root C11. So beta 1 hat is 0.7. We're checking if it is significantly different than 0. S came out as the square root of that value, because we in the previous exercise we already evaluated s squared. So the square root of that, if you take it, I think comes out as 0.606. 0.606 times the square root of C11, which is 1 over that SXX business. But SXX was, what was SXX? SXX is, I think we did it even earlier than that. Yes, it came out as a 10. Yes, so let's go all the way down. That one is 1 over 10 inside the square root. Okay, so yeah, if you calculate all this, I think it comes out as 3.65. Now, this is our test statistics. We need to check if that test statistic happens to be inside the rejection region. If it is, then yeah, so we reject the null hypothesis, and we can say that the slope coefficient, the beta 1, is significantly different than 0. So for that, we need to first find the critical value. At the 0.05 significance level, I think the value, the critical value, the t value, we need the critical value for n minus 2 degrees of freedom, right? So 5 minus 2 with 3 degrees of freedom. Okay, there you go. Okay, let's just write the critical value first. The critical value with 3 degrees of freedom. So basically what we have is a student t distribution, which is a distribution which looks very similar to the normal distribution. But so we are looking for the area on the tails. So this area is 0.0, wait, what was the significance level? 0.05, so which means this one is 0.025, and this area is 0.02, oops, 0.025, okay, 0.025. And so the critical values are what we need. So the critical value here and here, we can call them t minus t0 and t0. So if you just check the tables for the student's t-test, I think this number with 3 degrees of freedom comes out as 3.182. So this one is 3.182, and this one as a result is minus 3.182. And finally, check if this number falls into any one of these two rejection regions. Yes, our number is a little bit more than 3.182, so this one is 3.65, right? So therefore, yes, we the test statistics fall into the rejection region. So as a result, we reject the null hypothesis. And lastly, we are going to have a look at this. We would like to calculate a 95% confidence interval for beta 1. So that also is very straightforward, basically. So we want to reverse engineer what we did. So the confidence interval is calculated like this. At the lower bound of our confidence interval, we will have this beta 1 hat minus t, the critical value at the 0.025 significance level, times s times the square root of c11, comma, and up at the upper end, b1 hat plus t 0.025, s times square root of c11. Now we can just go ahead and plug in the values. So 0.7 minus the critical value, we found out it was 3.182 times s, which was, I believe, 0.606, and c11 was square root of 1 over 100. Oh, wait, 1 over 10, I think it was. And the same thing with a plus sign. 0.7 plus 3.182 times 0.606 times the square root of 1 over 100, close parenthesis. So this is the lower and upper bound. So as a result, this thing comes out as 0.7. If you do all the algebra here, that number I think is 0.610. So 0.7 plus 0.610. And yeah, so you guys can realize that. So the average is 0.7. So if you just think about it, so our average here is 0.7, and as a result, you go one standard. You go and check the critical value. So this is our confidence interval. We are 95% confident that that the beta 1 hat will be within this interval. So the true parameter, I should say, beta 1 will be within this interval, right? Yeah, so what is this? 0.7, if you subtract that, so that would be 0.09, is it? Yes, so let's call it 0.70 then. And on the upper hand, it is 1.31. There you go. So we are 95% confident that beta 1 will be within this interval, right? Does that make sense? And obviously, nowhere within this interval, so we are 95% confident of that. And look at the 0. So remember, in the previous exercise, we rejected the null hypothesis because 0 is outside this confidence interval. So this is our confidence interval. All right, so hopefully this was useful for you guys to finish your assignment as well. So yeah, so I will stop here. So in the next video, we will do all this in Excel, and you will see how fast it is.